Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Sorry, just give me 1 second. Okay, so starting with question 1. Draw the Lewis structure for methanol, which is H3COH. So first, let's calculate the total valence electrons of the molecule. So there is 1 carbon, which contains 4 valence electrons. There is hydrogens, so 4 hydrogens, each with 1 valence electron. And finally, oxygen, which has 6. So I'm going to draw carbon bonded with the hydrogens and bonded to the oxygen, which has the other hydrogen on its right side. So all of the hydrogens will have single bonds, and the oxygen will contain the 2 lone pairs. So if we count out all of the total valence electrons that I've drawn so far, if we recall that each bond contains 2 bonding electrons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plus the 4, so we have 14 electrons. So based on this structure, predict the hydrogen-carbon-hydrogen bond angle and explain your reasoning. So for the hydrogen-carbon-hydrogen, we have, I highlighted it there. So if we look at the carbon, there are 0 lone pairs, and there are 4 bond groups. So if we use the Vesper theory table, when you have 0 lone pairs and 4 bonded atoms, we have a tetrahedral geometry. So this is tetrahedral. And also using this table, we're going to use it to find the bond angle. So for tetrahedrals, it's 109.5 degrees. So for the second part of the question, we want to predict the hydrogen-oxygen-carbon bond angle? So I'm assuming they mean where oxygen is our central atom. So hydrogen, oxygen, carbon. So if we look at oxygen as our central atom, oxygen has 2 lone pairs and only 2 bond groups, so the carbon and the hydrogen. So again, we can look at our VSEPR table, and you can find it here. So when we have 2 lone pairs and 2 bond groups, we have a bent molecular shape. The electron geometry, however, is also tetrahedral. So its bond angle is still 109.5 degrees. So the junior tutor said that the central carbon atom has 4 bond pairs and no lone pairs for a total of 4 electron groups. Thus, the electron geometry is tetrahedral with bond angles of 109.5 degrees. The central oxygen atom has 2 bond pairs and 2 lone pairs for a total of 4 electron groups. Thus, the electron geometry is tetrahedral as well, with bond angles of 109.5 degrees also. Okay, so this solution is correct. Okay, on to question number 2. Is to determine the number of valence electrons in acetic acid, CH3COOH, and then draw the corresponding Lewis structure. So first, let's find the valence electrons. So there are 2 carbons, and each carbon atom contains 4 valence electrons. And we have hydrogen, which has 1 valence electron, and there are 4 hydrogen atoms. Then lastly, we have oxygen. So oxygen has 6 valence electrons, and we have 2 oxygens. So now let's just add this all up, and we should get a total of 24 valence electrons. Okay, so they already kind of hinted at what the structure might be. So we have a carbon with 3 hydrogens attached to another carbon that is attached to 2 oxygens and another hydrogen. So notice that this carbon does not have a full octet, so I'm going to draw a double bond. And now I'm just going to fill in all the lone pairs in the structure. Okay, so now let's double check to see how many electrons I've drawn. So each bond contains 2 bonding electrons, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we have 24 electrons on the structure. And this is the correct valence structure, or Lewis structure, sorry. And the answer is C. Okay, so the junior tutor said that the Lewis dot structure represents the arrangement of electrons, shown as dots, between atoms in a molecule. The atoms must follow the octet rule, or the tendency of atoms to prefer to have 8 electrons in the valence shell. The individual formal charge of each atom, as well as the overall formal charge of the molecule, must be satisfied. Calculating the total number of valence electrons, they also got 24. And distributing the electrons and replacing shared electrons with bonds, the Lewis structure for acetic acid is shown below. Yep, so this solution is correct. Okay, so question number 3. What is the Lewis structure for trithiocarbonate ion? So this is CS3, 2-. So first, let's find the total number of valence electrons in the molecule. Carbon has 4. And sulfur contains 6. And there are 3 sulfur atoms. And notice that the molecule has, or the ion, has a -2 charge. So I'm going to add an additional 2 electrons to our total number. And we have a total of 24. Okay, so now I'll draw my carbon as our central atom. And then I'll draw the sulfurs all around. And then from here, I'm just going to show all of the lone pairs on sulfur. So if I look at my structure and see what I've drawn so far, you'll notice that I do have 24 electrons in total if we remember that each bond contains 2 bonding electrons. Then so far I have 24. But since the carbon doesn't have a full valence shell, I'm going to bring one of these electrons down to form a double bond with the carbon. So now we have the following molecule. And these 2 sulfurs will contain a negative charge. So I can also draw different resonance structures. So let's draw this going down. It's because just to have enough room. And just with each sulfur containing the double bond. And lastly, we can have the leftmost sulfur as well, containing this double bond. Yeah, I did not plan out the space right. Those are all the different resonance structures as well. And if we look at the junior tutors' answers, they also wrote out all of the different Lewis structures you could obtain for this trithiocarbonate ion. So this solution is correct. Okay, so question number 4. What is the Lewis structure for aluminum trichloride? Or just aluminum chloride, actually. Okay, so aluminum chloride. Aluminum has 3 valence electrons. And chlorine contains 7. And there are 3 chlorine atoms, so we just multiply this by 3. And for the total number of valence electrons, this gives us 24. So let's draw aluminum as our central atom. And then I'll just draw all of my chlorines. And then draw out all of the lone pairs on the chlorine atoms as well. And if we recall that each bond contains 2 bonding electrons, if I were to count out how many I drew so far, I would have the 24 that I need. So notice that aluminum doesn't have a full octet, but in this case, this is okay since aluminum is one of the exceptions to the octet rule. So it's one of those elements that is satisfied with only having 6 bonding electrons. So this is our Lewis structure. And the junior tutor said that the number of valence electrons for aluminum chloride is 24. Aluminum is the least electronegative, therefore it is the central atom. The octet rule is satisfied for the chlorine atoms. Aluminum is an exception to the octet rule. It is satisfied when having just 6 valence electrons. Yep, so the solution is correct. Okay, so question number 5. Well, 2 resonance structures can be written for NO2-. Indicate the hybridization on the central atom for each resonance form. So first let's calculate the total number of valence electrons in this ion. So nitrogen has 5, oxygen has 6, and there are 2 oxygen atoms, so we multiply this by 2. And the ion as a whole has a -1 charge, so we're going to add an additional electron to our total count. Okay, so if we add this all up, we get a total of 18 valence electrons. So now let's draw our molecule. So nitrogen is our central atom, and then I'm just going to draw a single bond to each oxygen. So now let's show if I fill in all of the lone pairs. You'll notice that nitrogen does not have a full octet yet, so I'm just going to bring one of these electrons down and form a double bond with this oxygen. Okay, so this is one of the Lewis structures of the NO2- ion. And the second one will have the other oxygen having a single bond, and the rightmost oxygen now having the double bond. Okay, so this is the second resonance structure as well. So now we need to indicate the hybridization on the central atom for each resonance form. So the central atom is the same, so we just need to do this once. But if we look at nitrogen, you'll notice that it contains 1 lone pair, and it only has 2 bonded atoms. Okay, so we would now use our VSEPR table to figure out its hybridization, and also we can see the molecular shape and electron geometry. So when we have two bonded atoms and one lone pair, we get a structure that kind of looks like this. And the molecular shape is bent, the electron geometry is trigonal planar, and the hybridization is sp2. So I'll just write that down. Bent, trigonal planar, and sp2 hybridization. So the bond angles are 120 degrees. Okay, so let's see what the junior tutor said. The resonance structures are given below. Obtaining the steric number would allow us to determine the hybridization of the central atom. So the steric number is the number of lone pair of electrons around the central atom plus the number of bonds around the central atom. This is a different method. So note that multiple bonds are counted as 1. So since structures 1 and 2 have the same number of lone pairs and bonds around the central atom, both their steric numbers would be the same. It's equal to 3. Steric number of 3 would mean that nitrogen is sp2 hybridized. The nitrogen in structures 1 and 2 have a hybridization of sp2. Yep, so that's another method of doing it as well. It's pretty much the same thing. So this solution is correct. Okay, so question number 6. What is the Lewis structure of iodine trifluoride? So first let's find the total valence electrons in the structure. So in the case of iodine, there are 7 valence electrons. And for fluorine, there are also 7, but we have 3 fluorine atoms, so we take that into account as well. And we have a total number of 28. So now I'll draw my iodine with my 3 fluorines all around it. And I'll draw out all the lone pairs as well. So if we count out how many electrons I've drawn so far, each bond contains 2 bonding electrons, and then we have 6 in total for each fluorine atom, so I only have 24 electrons drawn. So for the remaining 4, I'm going to add them as lone pairs around the iodine. Now we're left with the following Lewis structure. Okay, so let's see what the junior tutor said. A Lewis dot structure is a representation of an atom, ion, or compound that shows how the valence electrons of the atoms are distributed as bonds, lone pairs, and sometimes radicals. Drawing the Lewis structure of a compound may sometimes need some trial and error, however, we can follow some guides and rules in drawing it. Okay, so step by step, determine the central atom. Typically, the central atom can create the most bonds. Sometimes it is given in the formula of the compound itself. Step 2 is to logically arrange the atoms. Thinking beforehand how many bonds an atom can create can be helpful. For atoms that follow the octet rule, the number of bonds an atom typically makes can be solved by subtracting 8 by the number of valence electrons of an atom. And step 3, connect, adjust the number of bonds if necessary, and check the rules if they're followed, redraw the entire molecule if needed. Okay, so let's skip down to when they answer the question, only iodine can exhibit expanded octet. Therefore, it is the most logical central atom because it can create the most bonds. 2. The skeletal structure would simply be an iodine atom in the center that is surrounded by the 3 fluorine atoms. Step 3. Since fluorine follows the octet rule, it would typically create a single bond only. The remaining valence electrons will be represented as lone pairs. Since there are 3 fluorine atoms, 3 valence electrons of iodine will be used to create 3 bonds. As a result, the remaining 4 valence electrons will be drawn as 2 lone pairs, and they got the following structure. Okay, so lastly, they calculate formal charge, which is also a good practice as well. So the equation for formal charge is equal to the number of valence electrons minus the number of non-bonding electrons plus or also minus the bonding electrons in the molecule divided by 2. So rule 3, all formal charges are 0. So this solution is correct. Okay, so question number 7. Draw the Lewis structure of carbon tetrabromide and answer the following questions. What is the total valence electron count? What is the central atom? How many bonds are on the carbon atom? How many sets of lone pairs are on a bromine atom? Okay, so this will help when we just write out the Lewis structure. So first, let's calculate the total valence electrons. So carbon contains 4 valence electrons, and bromine contains 7. So there are 4 bromine atoms, so we multiply this by 4, and we get a total count of 32 valence electrons. So now on the right, I'm just going to draw out the Lewis structure. So carbon is our central atom, and all around it, I'm just going to symmetrically draw all of the bromines. Now I'm just going to add the lone pairs. And from here, if I count out how many electrons I've drawn so far, so each bond contains 2 electrons, each bromine has 6 valent electrons, so I have a total of 32 drawn. So this is our most probable Lewis structure. Let's try to answer the questions. So what is the total valence electron count? We calculated it to be 32. B, what is the central atom? Carbon is our central atom. C, how many bonds are on the carbon atom? So if we count it out, we have 4 bonds. And then D, how many sets of lone pairs are on a bromine atom? So there are 3 sets of lone pairs. Okay, so let's see what the junior tutor said. The Lewis structure of carbon tetrabromide is shown below. Carbon has 4 valence electrons, bromine has 7, so there's 32 electrons. Carbon is the central atom, 4 bonds on the carbon atom, and 3 sets of lone pairs on a bromine atom. So I can verify that this solution is correct. Okay, so question number 8. Draw the Lewis structure of iodine Cl2 minus. So first, let's find the total valence electrons for this ion. So for an iodine atom, there are 7 valence electrons. And for chlorine, there is also 7. And we have 2 chlorine atoms, so we multiply this by 2. And the entire ion has a -1 charge, so I'm going to add an additional electron to our count. So now this gives us a total of 22 valence electrons. So if I draw iodine as my central atom, I can draw both of my chlorines on either side. And then I'll draw all of the lone pairs on the chlorines. So if I count out how many I've drawn so far, each bond contains 2 electrons. I've only written down 16. So now 22 minus 16 is 6, so I have 6 more electrons that I need to draw. So I'm going to draw them all on the iodine, since iodine is able to contain more than 8 electrons. So it's one of those exceptions to the octet rule. And this also gives a negative charge on the iodine. So we can calculate the formal charge and how I got that by using the following equation, where formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So let's calculate the formal charge of iodine. Iodine has 7 valence electrons. The number of non-bonding electrons is the total of electrons in the lone pairs. So we have 1, 2, 3, 4, 5, 6. And then the number of bonding electrons, so there are 2 bonds. So there are 4 bonding electrons divided by 2. So 7 minus 6 minus 2 is -1. So just to double check and see what our formal charge on one of the chlorine atoms would be. Chlorine also contains 7 valence electrons. There are 6 non-bonding electrons. And each chlorine only has 1 bond, so there's only 2 bonding electrons. So this gives us a formal charge of 0. So let me just do this in the same color. So this is why our iodine is the one that has the negative charge. So let's see what the junior tutor said. When drawing Lewis structures, the total number of electrons that need to be distributed is counted first by adding the valence electrons of each individual atom. If a formal charge is present on the molecule, this is also taken into account in the total number of valence electrons. Skeletal structure is first written by distributing bonding electron pairs, then the alone pairs are distributed until the octet is complete. Formal charges are added to the atom if the number of electrons does not satisfy the octet to indicate that an electron has been transferred, added, or removed. The structure with the least number of formal charges or has the smaller charge is the most stable Lewis structure. Okay, so there are 22 valence electrons. 4 are in 2 bonding pairs shared by the central iodine atom, and the 2 terminal chlorine atoms. The remaining 18 are distributed as lone pairs, 3 for each of the terminal chlorine and another 3 for the central atom. The Lewis structure is the following. Yep, so this solution is correct. Okay, so question number 9 is to calculate the molar mass of methanol. So methanol is CH3OH. So to find the molar mass of methanol, we would need all of the different molar masses of the atoms involved. So we would just find these values on the periodic table. So the molar mass of carbon plus 4 times the molar mass of hydrogen, since there are 4 hydrogen atoms in methanol. And then lastly, the molar mass of oxygen. So if we add all these values up, we get our total molar mass. So the molar mass of carbon is 12.01 grams per mole. Molar mass of hydrogen is 1.01 grams per mole. And the molar mass of oxygen is around 16 grams per mole. So if we add all these values up, we get a total of 32.04 grams per mole. Okay, so now let's see what the junior tutor said. And also this is option A, I guess. So option A. So given methanol CH3OH required molar mass. The solution is the molar mass of each element that makes up methanol is given below. So they summarize that carbon is 12, hydrogen is 1, oxygen is 16 grams per mole, and the molar mass is just the sum of the molar masses of the individual elements, also taking into account how many of each atom there are. You get 32 grams per mole. Yep. So this solution is correct. Okay, so now is question number 10. What is the correct systematic name of PCl5? Okay, so first let's analyze the name. We have phosphorus and chlorine, which are 2 nonmetals. So we know that the type of compound we have is a binary covalent compound. So when we name binary covalent compounds, the first step is just to name the first element. The second step, well, actually, also after naming the first element, you can use a prefix if there's more than one. But in our case, there's only one phosphorus. So the second step is just to name the second. Use a prefix. So even if we just have one, we still write in the prefix. for the second element. And then the ending is you just add "-ide". So in our case, first step is to name the first element. So we have phosphorus. And there are 5 chlorine atoms. So it's going to be penta. And then we name the second element fluor. And then instead of "-ine", we put "-ide". Phosphorus pentachloride. Okay, so I'll also summarize all of the different prefixes. So when we have one atom, we use the prefix of mono. 2 is di. 3 is tri. 4 is tetra. 5, which was our example, is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. And 10 is deca. Okay, so let's look at all the options they give in the question. Phosphorus chloride. This is incorrect since we don't know how many chlorine atoms there are. Phosphorus pentachloride, so that is our answer. Let's just write that down. Monophosphorus chloride. This is incorrect since the prefix is on the first element instead of the second. Pentachlorophosphorus is incorrect as well. Pentaphosphorus chloride is also incorrect because that's saying we have 5 phosphorus and like 1 chlorine. So that's incorrect as well. So the correct answer was B. So explanation, the naming of a binary compound is simple. Binary covalent compound. The first name is the same as the element name, while for the second name we change it into "-ide". So example, fluorine will change to fluoride. We also add a prefix to determine how many of the element is present. So for PCl5, it's named phosphorus pentachloride, so the correct answer is B. Yep, so this solution is correct. Okay, so those are all the questions for today's session, and if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, go ahead and give it a thumbs up and a like, and you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.